All right, effects on equilibrium here. Let me move this over, sorry. It's in the wrong spot, there we go. Now we're looking at pressure and how pressure affects the equilibrium system. Well, you must look at the number of moles of the gases on each side of the reaction. Obviously, the pressure effects are only going to happen with systems of equilibrium that have gases in their reactants and products, because gases are really the only ones that are going to be bouncing off the walls of the container and causing pressure. Another thing to talk about too is, let's see here, see if it'll, nope, it doesn't want to advance yet. Counting the number of moles on each side, and you do that based off of the balanced reaction, use the mole ratio or the mole coefficients in the balanced reaction. You're going to increase the pressure, saying if you increase the pressure, the reaction proceeds to the side with the least number of gaseous moles. So least here. Increasing the pressure, so if the products have the least number, it would shift towards the products. If the reactants have the least number of moles, it would shift towards the reactants. It's really dependent on how many moles are on each side. Decreasing the pressure proceeds to the side with the higher or greater number of gaseous moles. Okay, so decreasing, we're going to go to the side that has more moles of gas. General idea there. Now, some of the times it's phrased not just in terms of pressure, sometimes it's phrased in terms of changing the volume of the vessel. So if you change the volume of the vessel, you're still at the same temperature, because remember, equilibrium, pretty much all of these are run at a certain temperature. If you change the temperature, now you're altering your K value, so that's a totally different story here. But Boyle's law will apply. Anybody remember Boyle's law? If you decrease the volume, what's going to happen to the pressure? Yes, the pressure should increase. Remember, this is an inverse relationship. So if you decrease the volume, the pressure should increase. Okay, if you increase the volume, then the pressure is going to decrease. Inverse relationship there. One other thing to note here, addition of an inert gas. The noble gases, anything that's not going to react with either the reactants or products in the equilibrium system. And we know noble gases are already, stable on their own, so they don't really react with anything. But if you were to insert some inert gases into the reaction vessel, it does not do anything to the equilibrium position. All it's actually going to do is increase the overall pressure of the entire system. But you're not going to have any shifting of the moles because it's not reacting with the products or reactants. So the overall pressure, the partial pressures of the individual gases are going to stay the same. The ones that are in the equilibrium reaction, and then of course the noble gas that's been added will add its own partial pressure to the mixture, and then the overall pressure would increase. So the equilibrium position does not adjust based off of that. That's the trick one that they put in here occasionally, like throwing in an inert gas. You think, oh, more moles, so it shifts to the least. No. Adding an unreactive gas to the system, the equilibrium position stays the same or has no change. Alrighty, so let's look at an example here. Must look at the number of moles of the gas on each side of the reaction. So before you even begin trying to decide any of this, the first thing you should do is count. We have 3 moles of hydrogen, we have 1 mole of nitrogen, so there's a total of 4 moles of gas on the reactant side. We have 2 moles of the ammonia, so that means there's 2 moles of gas on the product side. That is the first thing that you should do before you begin. Now you have the established relationship of number of moles, and you can decide which way it's going to proceed or shift. So if we increase the pressure here, which way is it going to proceed? It's going to proceed towards the products. Exactly. The products have the less number of moles, so it's going to go to the side with the least number, shifts towards the products. Okay? Now, decreasing the pressure, this particular case, once again, looking at the numerical value of the moles of gas, which way would it proceed? Towards the reactants. Very good. So in this case, it's 2 moles to 4 moles, so it's going to proceed to the side that has more moles of gas. If you decrease the pressure, it would go towards the reactants in this case. Exactly. Now, if we decrease the volume of the vessel, all right, we're going to take the volume, we're going to decrease the volume. What does that tell us here? What's going to happen to the pressure? Pressure is going to increase. Very good. So if we increase the pressure, which side should it shift towards? Go towards the product with the least number of moles. Okay, towards the products. Exactly right. And increasing volume, what does that do to our pressure? It's going to decrease as well, or I mean, it's going to decrease because of Boyle's law, where the volume increases, pressure decreases. So in this case, it should go towards the side with the most number of moles of gas, which would be towards the reactants. Last but not least, how about we add in some neon? What does that affect? How does that affect equilibrium? Doesn't. No change. Exactly right. So this is what I would write here. No change. Or you could put, you know, stays the same. Either one would be a appropriate answer. Any questions on pressure? All right. Answers. There we go. The Haber process. So transformation of nitrogen and hydrogen into ammonia. This is a very important application that's noted also in many textbooks and online references for equilibrium, because we need ammonia to be put in fertilizers for agriculture. Of course, production of food is very important. And you want to maximize the output of the ammonia from the nitrogen and hydrogen gases that get fed in there. So as you can see, like this is a diagram showing where they put it into a heater, of course, increasing the temperature to a certain amount, and then of course they adjust the pressure and they adjust for, see they have a compressor here. You can see the compressor, you can see there's heaters, and they have different, a heat exchanger here. And then over here to the right, eventually when they get the reacted stuff, they have the condenser that cools it down into ammonia liquid. I just wanted to point out to you, see that in industry, they have it set up to manipulate the equilibrium position using LeChatelier's principle, where they figured out how to maximize the output of the ammonia. So, you know, it's still not 100% yield, of course, okay? But they have figured out, you know, the right figures to maximize the resources of the reactants and produce as much product as possible. So the next graphic kind of shows, well, a little bit more detail. This one is from the, I think this is from my old textbook from last year, but there should be a similar one in your e-text, but also showing you that you have, you know, heat exchangers and you have, you know, compressors and things going on there. And this one's also showing the presence of a catalyst, which we're going to talk about in just a minute, what a catalyst is. But lots of process going on here in order to maximize the output of the liquid ammonia. So reactions that have equilibrium positions, because, you know, they don't go to completion, they go to an equilibrium position. Some of these components, you know, are needed and have to be generated in factories, in industry, and they use LeChatelier's principle, of course, to adjust it to keep getting and go for the output that they want. And that's a nice application. This one shows exactly that. There's other ones, of course. Becomes a nice balancing act to make sure you get the maximum output of your desired product. So here, I liked this graphic because it kind of shows the different percentage of yield that they're getting at different temperatures and different pressures. So obviously this one has been tested multiple times to maximize the output of the ammonia. And it's showing here, you know, this block right here at 500 ATM, which is very high pressure, by the way. 400 temperature here, that's when they're getting the 60.6% yield. And as you can see, if they continue to increase the temperature, they end up getting less yield. And if they decrease the pressure too, they get less yield based off of those percentages there. So I thought that was a nice, clever graphic to kind of show you, and also realizing that for these equilibrium type reactions, like the idea of getting a maximum output of 100% yield is very unlikely. But manipulations are done with LeChatelier's principle to get as much percent yield as possible. So that brings us to catalysts. Catalysts lower the activation energy for both the forward and the reverse reactions. I don't know if you remember on the energy diagrams here, you know, here's our reactant line, here's our product line. Before we were looking here at delta H, which is the products minus reactants, the enthalpy change, right? Here, and we'll get more into catalysts when we talk about kinetics, because that's about speed of reaction. But the activation energy goes, you know, from the top of the transition state to the reactant line. That's the activation energy. So a catalyst, of course, lowers the activation energy. We saw that in also our How to Get a Date for the Dance video, that it repositions the molecules so they collide better, orient better, and lowering that energy needed for the collision to take place. What you see here is the hill is lowered in both directions. I mean, it's the same whichever direction you're going. So it speeds it up equally in both directions. What that does for us, though, in terms of equilibrium position, is pretty much nothing, because the equilibrium, the forward and reverse rates, it's quicker to getting to equilibrium, but the composition or the amounts of the reactants and products, that proportionality of K, that does not change. It remains the same. It's just speeding up the reaction, you know, in the forward and the reverse to get to equilibrium faster. So that equilibrium position, or that equilibrium composition where it's products over reactants, the law of mass action, that K value, that one actually remains the same. Catalyst does not affect the equilibrium position. So this is another thing they like to ask. You know, along with the inserting the noble gases or the inert gases, this is another one that trips people up. So if ever asked in a multiple choice question or for response, adding a catalyst does not affect equilibrium, so equilibrium position would remain the same. And when it says equilibrium composition, it's really talking about the position, which is the products over reactants. Products over reactants, which is the amounts of the concentrations when the forward rate and the reverse rate have equalized. Any questions on catalysts? So anytime you see adding a catalyst for equilibrium, put no change, stays the same.